Thank you guys for joining to this new edition of the research seminar here in MODEMAT. Today we have the talk by Christian Kreuzer. Christian is professor at the Technical University in Dortmund, and he's a specialist in numerical analysis with several applications, mainly in non-Newtonian fluids and also in optimization and optimal control. So Christian, thank you for accepting the invitation. Thank you for joining us in this seminar, and well, the audience in the MODEMAT here in Polytechnic is yours.
Okay, so thank you very much for the opportunity to give a talk in your seminar. So actually, this is my first result on optimal control, and I thought that's maybe a good opportunity to present this in your seminar. So I think most of you are kind of involved with optimal control, so parts of it will be known to you, but I'm trying to access this topic from the point of a numerical analysis. So my main concern here is to understand the quasi-optimality properties of the approximation to the optimal control problem. So yes, maybe I should also mention that this talk is joint work with Fernando Gaspos, who is since this month back in Santa Fe, Argentina, and Andreas Fecha from the University Milan, and Winifred Wollmer from the University of Hamburg. Okay, so the outline is as follows. First of all, I will introduce the constraint optimization setting, and then we have a look at different discretization, so a variational discretization, first without a control discretization, then with control discretization, and then in the last part we will have a look at what happens when we have control constraints. But before we enter this topic, I would like to say something about quasi-optimality. So this is one slide about quasi-optimality, and we go through it very slowly. So in principle, because of this presentation online, I removed all my overlays. So you will see the entire slide, but maybe you should not read it directly. Okay, so we start from the setting with two Hilbert spaces, a Hilbert space V and a Hilbert space W, and finite dimensional finite element space, say VH and WH here. And we have a bilinear form, which is this B here, which acts on the product space of V and W, and is non-degenerate on the discrete spaces, on the product of discrete spaces. What do we mean by non-degenerate? The first thing is we assume that the bilinear form is continuous. Okay, that's just continuity. And the second thing is that it is insubstable. That means that the operator which is associated with B, which maps B onto the dual of W, is injective and surjective. Okay, so it's a one-to-one map. And well, this is the notation for that. So we have an inf and a sup over the spaces BH and WH, and this bilinear form here divided by the norms, and the same with interchange rows of W and VH. So that is the same as this for the dual operator, so to say, or the adjoint operator. Okay, and if we have something like this, such an inf-sup condition, then we know that for any function u, there exists a unique Galerkin projection. Galerkin projection is just defined by that. Okay, that's just a Galerkin solution. And this Galerkin solution satisfies a quasi-optimality condition. Okay, that is a generalized version of the Sears lemma. Okay, and in the Sears lemma you would have this, for example, by coercivity, and we have it just by insubstability, which basically means that the lowest eigenvalue of the linear operator is bounded away from 0. And what one can show then, and this is, I think, maybe, so I don't know how much you are in numerical analysis, but this is numerical analysis typically know it, that the subconstant, the quasi-optimality constant, sorry, which we have here, is actually there's an exact representation of it, but it's an abstract exact representation of it. But it is bounded by the continuity divided by the subconstant. Okay. However, this is an upper bound. This is an upper bound, and this is immediately clear to you because when you see at the quasi-best approximation here, you see that there is no norm W involved at all, neither in the definition of UH, because this is for all WH, nor in this expression here. Okay, so this quasi-optimality constant is not depending on the norm you're using on W. Okay, however, as you can see here, this subconstant may depend on or depends on the norm you're using on W, so that is always an upper bound. Okay, but this is maybe a technical detail here, but okay. But maybe some not very important part later on. I will mention it again. Okay, so this is quasi-optimality. Okay, and now we have a look at the optimal constraint problem. Okay, so I'm to minimize this expression here, subject to a state equation, which is this one. Okay, and we have here not a bilinear form B, but we call it A. Okay, but the bilinear form A here satisfies also a non-degeneracy condition here. Okay, so that means that it's just, you can uniquely solve this. Okay, and then we have some operators involved here, and one operator is the control operator, which maps Q, so from the control space Q into the dual of V2, so V2 star. And this is linear and bounded on an Hilbert space, so on the control space, which we also assume to be in Hilbert space. Then we have some desired state UD here in an Hilbert space W, and a linear and bounded observation operator, which maps V1 to W and appears here at that point. And then in additional, we have a cost parameter or stabilization parameter, and we call it Tikhonov cost parameter, alpha. Okay, and before we enter the theory, we just have a simple example, and this is kind of, we always pick up this example if after I've presented some theory, we will always pick up this example and we'll have a look what it means, what I told before. Okay, so we have this simple distributed control problem. So we minimize this expression here. We have U in H01, so the observation map is just the canonical embedding, so you can see here, and we we have Q, the control, in L2, and this means at that point that because we see the Laplace operator mapping from H-1 to H1, this is the C is then just the canonical embedding of L2 into H-1. Okay, so I think this should be well known to you that is maybe one of the most simple optimal control problems. without any control constraint or something fancy like this. Okay, so by Lyon's theorem, we know that the unique solution or the control problem, the optimal control problem, admits a unique solution, and it is a solution of this first order system here, where the A is just a linear operator which is induced by the bilinear form, this small a here. And we have, in addition, here the dual state P involved with the operator dual to A. Yeah, but I think this should be known. Okay, so anyway, if something is not known to you, or if you have some questions, then just ask. Okay, and what we can do now is we can reduce the optimality system and only use the state and the adjoint state by just inserting this equation up here. Okay, and this gives us this relation here. So this is our optimal control problem. Okay, now let us further investigate this. So we are looking for solution U and P. This is the state. This is a dual state in V1 and V2, such that these conditions here are satisfied. So that is just a copy from the previous slide. And this we can now write as an operator equation by, well, we scale this equation by, no, the second one, sorry, we scale this equation by 1 over alpha and get this one. And we add just this equation. This is just the second line here. Okay, and then because we would like to have a nice presentation and nice operators, we just rescale this dual state by 1 over the square root of alpha and call it Z. Okay, and if we introduce this Z here, we get rid of the 1 over square root of alpha here, and the 1 over alpha here becomes 1 over square root of alpha, and then we have a nice symmetric operator. Okay, well. Okay, now we can reformulate everything in a bilinear form, okay, in a bilinear setting. And in fact, as we have seen on the very first slide for the quasi optimality setting. So we call the spaces V and W from the very first slide. We identify them, and this is just the product between the V1 and the V2 space. And then our bilinear form is just B of x phi is A of x phi plus 1 over square root of alpha. And then we have a new operator Cx phi here, which appears from there. Okay, this is nothing else than writing this here as a bilinear form. Okay, you have an operator equation, bilinear form. It's just a rewriting. Okay, we have here, maybe this I should mention here. This is just, we have some abuse of notation here. We call this the same bilinear form, whether we use it to the single variables or to the product of the tuples of the functions. And we have then this C, and this is called for reason C because we assume later on that the operators involved are compact. Okay, and then our rescaled and reduced variational problem is just reading like this. This is nothing more than the operator equation, just rewritten as a bilinear form. Yeah. So we are looking for an X such that for all test functions phi, this is satisfied and the UD is the data. Okay, and now we want to kind of verify the conditions for the quasi optimality. First of all, there was the continuity, and to this end, we need to choose some norms, and we choose first of all for the state and the dual state, just simply adding up the norms in V1 and V2, and we choose a constant m, which is just the max of the continuity constant of the control and the observation operator. And then one can estimate the bilinear form, and well, we have just chosen then this norm on phi. There's a subscript alpha here because it depends on alpha, such that we get a constant one here. Okay, that's just a choice. And this operator, this norm, or that's not a norm, it's a semi-norm. Only altogether this is a norm, right? This is IC stands just for this I operator and the C operator here. Okay, this is just put into the norm. Okay, and well, and then so we have continuity, and now we can prove insubstability, and with a bit involved constant here. So there's a lot of other constant involved here with a constant capital L. This M was just the max between the observation and the control operator. We can prove that the inf sup of the bilinear form with respect to these two norms is 1 over kappa, and then you have MA, so the inf sup constant of A divided by the continuity constant of A. Okay, and so now that's kind of, you see already where we're heading to. We would like to compare the properties of the optimal control system with the properties of the state equation or the state operator, okay? Because we expect that we cannot do better than for the state equation. And you see when you have a look here, this L deteriorates like 1 over square root of alpha, but of course this cancels out. Okay, if alpha goes to 0, this is canceling out here. So the whole constant basically behaves like 1 over square root of alpha. Okay, so this you can see here. So the limit is basically this. So this cannot improve in general. And here's a very basic example, a finite dimensional example with state operator here, then the observation operator, control operator, and you get the bilinear form here. And that's some computations here, but what we can prove is that indeed the inf sup constant is bounded by the square root of alpha. So we cannot do better than proving that this is bounded, or I mean, if we can bound it from below by square root of alpha, then we are pretty much fine, up to a constant, of course. That's just the dependence on alpha. So we cannot do better with this choice of norms here. And the reason for that is essentially that we have variables here that have a scaling and parts that do not have a scaling. And when you do compensate them in a certain way, then you end up with the square root of alpha. Okay. So now that is the basic setting so far. And now we enter the variational discretization. So we choose finite dimensional spaces, V1H, subspace of V1, V2H, subspace of V2, and we assume that this operator, so A on the discrete setting, is not degenerate, so means that it's continuous and insubstable. Think of the Laplacian, then just by coercivity you have everything, all right? So what we do have from this setting is that for the state equation, Okay, for the pure state equation, the Ritz projection is a quasi-best approximation. That's just, when you think about the Laplacian, it's Sear's lemma. Okay, so we have a best approximation constant, which we call mu h. Okay, it's not the new h. The new h is the best approximation constant. Later will become the best approximation constant for the optimal control problem. So this is the best approximation constant here. And now there's a cosmetic trick. Okay, and now I recall that I in the very first slide mentioned that that we have an explicit representation of the quasi optimality constant, and the quasi optimality constant is not depending on the norm on the test space, but only on the norm on the trial space. And this is the cosmetic trick. You simply can choose the norm on the test space by this, and then you end up also for the dual operator with exactly the same best approximation, quasi-best approximation constant. Okay, that's a bit of a trick, but this is not very much relevant, but makes the analysis a bit easier. It's not very much relevant because we're assuming a well-posed state equation here. We do not care about the state equation, we care about the optimal control problem. Okay, so we assume everything is fine here, but it's quite nice when you have the same constant for test approximation and trial approximations. However, if you think again about the Poisson problem, then anyway it's the same. Okay, so again, now we would like to look at the discretization, and here we are just using the variational discretization of Hinze. And this means that we simply insert, so we don't have a control discretization, so we simply insert, or we solve this bilinear form here and satisfy it on the discrete level. So we know that the discrete reduced optimality system has a unique variational solution, which we call XH here. And this means, by the way, I didn't tell you this before, but if a bilinear, so the linear problem or the variational problem has a solution if and only if the bilinear form is not degenerate. So if and only if we have this insubstability and so on and so forth, right? And then one can also identify a control to that, and this is why it's called the variational discretization. The control is not necessarily a discrete function anymore, so but we can hopefully compute it, and is the unique solution to our original optimal control problem. Okay, so now I told you already that, and you know that this problem is well posed. So it's the bilinear form is non-degenerate. So when a bilinear form is non-degenerate, we know that there is a quasi-optimality constant. Okay, so there is a nu. We know that there is something like that. Now the question is, what is the nu? And there, of course, as often, then is not only one answer. So the first answer is, yes, well, we learned from quasi-optimality at the very beginning, we need to satisfy the in-sub condition. If we can satisfy the in-sub condition, we are fine. And we have quasi-optimality, and the in-sub constant is an upper bound for the optimality constant. Okay, so what happens here is, and this is what I told you before, we would like to relate everything to the situation in the state equation. Okay, how much worth is the approximation property of the optimal control problem with respect to the state equation? And so this is the quasi-optimality constant of the state equation, and this is the amplification of this constant. Okay, now we can see this. This looks very much as the subconstant of the continuous problem. Okay, so it's pretty much plausible. And this deteriorates, again here, this constant here is appearing a second time, and this deteriorates like 1 over the square root of alpha. Okay, this already is an improvement about existing results where the constant deteriorates like 1 over alpha squared or 1 over alpha to the 3/2. Okay, but this is not the end of the story, because when we swap, you remember the operator equation we had recently, when we swap the rows of the matrix, this very much looks like an operator with definite diagonal and some parts here on the off diagonal. And now this is quite often the case, and also in our toy example, we have that the control operator and the observation operator are compact operators. So what we have here is a compact perturbation of a diagonally dominant operator. So we have a nice operator here on the diagonal, which is our state operator, say, and we have a compact perturbation. And now we're going to use some arguments by Schatz for the Helmholtz equation. In a Helmholtz equation, you have a similar situation. You have the lower order term, which is a compact perturbation. And a compact perturbation usually means that it's converging higher order. And we will see this in a minute. So, well, I did, okay, here's so first of all, I jump now in the last line of the slides. What we do, we would like to estimate this term here. So this is the error, x minus xh. Okay, what we do is we bound this by x minus rhx. Rh at x is the Ritz projection of h. So this is just the Ritz projection you can see here. Okay, so this is the quasi-best approximation for the state equation. So we use a triangle inequality, and then of course we need to further estimate this. Okay, and when we do that, we start from this. This is what we want to estimate, this part here, and we use the subconstant to go here. This is just in subconstant. And then we use that xh, and rhx basically leads to the same right-hand side for A. And the only thing which is different that we have here this compact operator, so that the observation and the control involved. Okay, but the A operator cancels out. So here we have some compact, so this is our compact operator when we assume that the observation and the control operator are compact, and we simply estimate this by this norm we already had before in the definition of this alpha norm for the test space. Right, and the question now is, how fast is this converging? How fast is this vanishing? And to this end, we need, well, I mean, there's a non-quantitative result we have in the paper, which simply says this is vanishing faster than that guy. Okay. But we can also make it quantitative, and what we assume here now, this is now we try to quantify compactness and smoothing property of the state equation. Okay, so we assume that our state and dual state spaces have some kind of Sobolev regularity, and we have some Sobolev norms here, and the the control operator maps, and this maps the control space into the dual of V2, and the observation maps into W, and they satisfy some additional regularity. So you say, well, we have an example on the next slide, and then we have some regularization that the operator A is mapping into, if you have a bit more regular data, it is mapping into a bit more regular space. Okay, that's basically it. And we have it, then we need to have some approximation property. So if we have a bit more regularity, then we want to get out some H. Okay, that is just the space discretization parameter here. So under these assumptions here, we can quantify how much faster the compact terms are vanishing, and we can prove that this is the best approximation for the optimal control constraint. This behaves like 1 plus kappa. That's the same kappa as before from the subcondition, but then times O of H to the power of delta. Okay, so this means that when you let H go to 0, then this approaches the quasi-optimality constant of the state equation. Here we have our example again, our distributed control example. So in this case, the VI is just H01, both of them, right? And this means that from the previous slide here, we have this SI here. Both of them are 1, and we have delta equal 1. So delta equal 1 because the control and the observation space is L2. So this is H1 minus 1, and the minus 1 is the delta. F is in L2, so the right-hand side is in L2. So, and then if we apply this operator, then we get, on a convex domain at least, H2 regularity, and this is and this can be bounded by the L2 norm of F, and this is again H1 minus 1. And then of course, if we use piecewise linear continuous elements, we get that the H1 norm can be bounded by H times the H2 norm. Okay, and this means that in this case we have, for the best approximation constant, the best approximation constant for the state equation times 1 plus this kappa times O of H. Okay, so, and when we have a look at this kappa bar here, by the way, the kappa bar the only reason why it has a bar there is because before it was a mu h. So the quasi optimality constant was depending on h, but now we take the worst case, mu h, and that's why it's with a bar. Okay, but this behaves like 1 over square root of alpha with respect to alpha. And so in the limit, it behaves like this as alpha goes to 0. This means that when you are interested in letting alpha go to 0, or when you want to have a best approximation constant which is independent on alpha, you need to choose h small enough, then the best approximation constant is independent of alpha. Okay. Then let's go next into the control discretization. The control discretization is basically a non-conforming approach. So we assume that we have an approximation, an operator approximating the C star. And this can be then simply handled by a so-called strong lemma. So the error which we have here is bounded by the best error plus some consistency term. And now everything which when we want to prove pure quasi-optimality, we need only to estimate this consistency term here. And the first observation is that that non-asymptotic quasi-best approximation is only possible when these norms here coincide for all discrete functions. And this is very, I mean, although of course you cannot say it's not possible, but it's very unlikely to happen. So a non-asymptotic quasi-best approximation is basically not possible to prove in this situation. But under some assumptions, under the assumption converging was a certain rate to 0, we can prove asymptotic quasi-best approximations results as before. So this is our assumption. So we basically assume that this is converging fast enough. Okay, it's kind of, it's obvious, right? If this is converging faster than the best approximation error, then you're fine. And we also assume that these operators are uniformly bounded into this space. Okay, this is okay. And then we can prove this quasi-optimality constant, but note here that there's an additional alpha here, because I mean we had the 1 over square root of alpha coming from the kappa, and there's an additional 1 over square root alpha here. Okay, so this deteriorates like alpha, and the reason for that is simply that we have a 1 over square root of alpha here. Okay, so you cannot avoid that. Okay, again, our example. In our example, we assume linear finite elements as before, and we assume that for the solution X we have that is optimally converging but not better than optimal. Okay, so it's vanishing like H. Then we discretize the control by piecewise constants, so we get that the CH operator is just the projection into piecewise constants of the operator C. And then by duality, we can prove that this is bounded by C1, a constant C1 times H squared. And now we are using this property and take one of this H and say, okay, this is a lower bound for the best approximation operator, for the best approximation quantity here. Okay, and this means that in this case, the above conditions, so the conditions from the previous slides, hold also with delta equal to 1. And then finally, we have a short look into the control constraints. And the control constraints is the setting as before, but we have a convex set, non-anti-closed convex set K in our control space, and then our optimality system is, as you can see here. So the only thing is changing, what is changing is that the control is the projection into the convex set K. And here's just, again, here's just the definition of the projection operator into the convex set. Okay, in this situation, we can also reformulate the optimality system and reduce it and rescale it as before, and we end up with this system here, where this form here is not bilinear anymore. Okay, because the operator C, which you can see here, involves here this projection onto the convex set. Okay, so this CK and so also the BK are not linear in the first argument in general. Okay, and so we need to have some, well, we need to tweak the situation a bit, and we introduce a metric. This is just this dk alpha. It depends on k and on alpha. which is just the norm of the state in the dual state. And then we have here a second term, and the second term is the same thing as before. This is this IC norm we used before. So in principle, this is the alpha norm or replacement for the alpha norm. The only difference is now we have here this projection operator. Okay. And for this metric, we can still prove continuity, and we can also prove insubstability. Okay. The constants are exactly the same as before. And with this, we can directly get, using the same techniques, almost the same techniques, sorry, as before, we can prove quasi-best approximation, but now in this metric. Okay, now in this dk alpha, not in the norm anymore. And the reason for that is that, and this is also the reason for this +1 here, by the way. Typically, when you do this, there's a trick by Zhu and Tikhonov, because typically before, so in the Ladyshenskaya, Babushka, Bretzi theories and everything, you typically have continuity constant divided by a subconstant +1. And the reason for this +1 is that they estimate this operator by 1 plus the norm of RH. But you can prove for a proper projection, you can prove that these two norms are actually the same. Okay, but this only works in a Hilbert space setting. So for Hilbert norms, now we have here a metric, and for a metric, you need to use the triangle inequality. That's the reason why the +1 happens here. Okay, this is the non-asymptotic quasi-best approximation. So what's about the asymptotic quasi-best approximation? And for the asymptotic best approximation, we recall that we need to, again, estimate the distance xh to the Ritz projection. And the proof is basically exactly the same as before. We use insubstability. Then here we enter the x. This is canceling out. So the A forms are canceling out, and we end up with the control and the observation forms. And this can be then estimated by that term, right? And again, we have this term here, which is a compact term and is of higher order. So, and now we are using the following. So this is as before. So this distance here can be estimated by that. That is what we have seen on the previous slide. And then we can use the theory from the non-constraint case and estimate then this here is higher order because of the delta compactness. So, and now we take this norm, use a triangle inequality, and estimate this by that guy here. And then we can enter this estimate and have here also the best approximation. And combining everything proves, again, a quasi optimality constant nu, which is bounded by mu h. And here you have a 1 plus the capital M. And here, this is the only difference to the one with the unconstrained case. You have 1 over square root of alpha. But in this case, it is not fully clear to us actually if this is sharp or not. So the other cases are essentially sharp. In this case, it's not fully clear to us. This comes from, this is a technical artifact of the proof. It can be that we could get rid of that. And this also behaves like 1 over square root of alpha. Okay, so we have here an additional alpha dependence. Yeah, and this comes from this additional dependence of this norm here, because before we could do everything for that norm, and now we have to involve this metric here. Okay, and with this, I would like to end the talk, and just here in a very short presentation, all results I have presented so far is if you go for variational discretization with continuous control action and observation, so there's no compactness assumption here, then we have a non-asymptotic quasi-best approximation constant, which behaves like mu squared over square root of alpha. In the case of a variational discretization with compact action, this I didn't show you, but I mentioned it, we can prove that the second term is converging faster. So it is vanishing as h goes to 0, but we cannot quantify it. But when we can quantify the compactness and the regularization property of the problem, so we have this delta compactness and delta regularity of the state equation, then we can quantify the how much faster this term is converging. And well, in this case, it is converging with h to the power of delta faster than the best approximation error. The same for control discretization. So if we have a delta approximate control action, so that means that this consistency error vanishes fast enough in all these conditions. And then finally, we have the result for the constraint control, where we also have higher order convergence here. So meaning that when you fix the alpha and you let go h to 0, then essentially you have the best approximation, the quasi-best approximation constant from the state equation. And on the last slide, I have all mentioned literature, including the results, which contains all the results I mentioned so far. And with this, I would like to thank you for your, what do you say?
Attention.
Attention, yeah, right. I just forgot the word. Something. Yeah.
Thank you, Christian, for this very interesting talk. And it's time for questions and comments. So.
Can I start, maybe?
Yeah, of course. Go ahead.
Christian, this analysis, this asymptotic analysis is based on a priori error estimates, right? I don't know if you can do a similar analysis using a posteriori error analysis, looking forward to use these estimations as a tool to adaptivity. I don't know.
Well, actually, we started actually doing that. Okay. And what you can do, that's quite interesting, is so first of all, without quantifying all this stuff, there are some quasi-optimality results, quasi-optimal convergence rates for adaptive methods available, which are actually using this. Okay, but they did not. I claim they did not know. They're using what they do. They use a quasi-orthogonality of the error. So an orthogonality which appears as h goes to 0, and this is in the same spirit of what we have here. This is one thing, and the other thing is what you can do in the a posteriori analysis. In the a posteriori analysis, you also have that basically you have. It's a bit different. Maybe I go to this slide here. This best approximation constant here. This is depending by the continuous continuity constant divided by the best approximation constant. So that's an upper bound. For the a posteriori analysis, you have here the sub constant of the continuous problem. That's a basic difference. Okay. So now what we can prove is also that that as h goes to 0, this efficiency of the efficiency index of the a posteriori estimator is converging to say 1. Okay, so to the efficiency index of the state equation, of the a posteriori estimate for the state equation. And now when you think about the operator, well, I don't know where it was. You know, we had this this IC norm, so this this compact difference which we wanted to estimate by the best approximation error, which is essentially, when you think about our top example, then it's just the L2 norm of the control and the L2 norm of the state, right? And this you can estimate. This you can estimate by an L2 error estimator. Okay, so you can even in some situations you can even hope for quantifying the best approximation or the how much how fast the efficiency index converges, or how close it is to the optimal efficiency index. You can even quantify a posteriori. Okay, so you can simply apply an L2 error estimator. I mean, there are then some restrictions in which situations you have L2 error estimates and so on and so forth. But in principle, that's doable, yeah. And then you get, of course, much sharper bounds. But you have the two versions. Again, you have that, okay, asymptotically you're converging to the constant of the state equation. But you can even quantify this and get a reliable bound in some situation, not in all. I mean, this is then strongly depending on the problem you're looking at.
Mm-hmm.
Okay.
Thank you, Chris.
You're welcome.
Are there more questions or comments?
Hi, I have a question. Maybe it's just a naive question, but I was wondering if in the original problem, have you tried, or what would happen if you try the L1 norm penalization instead of the L2?
Well, I mean, if you use the L1 norm, you mean here?
Yeah, exactly.
Well, then you're leaving the Hilbert space setting, and then
yes.
you're ending up with non-reflexive spaces. So I'm not so sure if the analysis will stay that nice. Then we didn't look into that, but I think that is well. I mean. You have to think about what I was presenting in a very basic research, so foundational research. This is not addressing real life problems, right? But it is explaining how problems. Though I would expect actually that when you think about a reflexive Banner space setting, so if you do not drive P to 1, so this maybe work still, right? Okay. I didn't try, but it might work still, right? But with the L1 setting, I don't know. That is things are getting really difficult.
Okay, thank you.
Welcome.
Are there more questions or comments? Okay, if this is not the case, Christian, thank you again for this very, very interesting talk. As I am saying to all the invited during this time, hopefully we will have you here in Quito sometime. You are always.
Oh, that would be great.
Very welcome here.
I was never in Ecuador actually.
So we will be very happy to have you here. Thank you for this talk, and thank you for accepting the invitation. Gracias a todos por haberse conectado. Y bueno, vamos a tener una para de unas 2 semanas. Luego ya regresaremos nuevamente con el seminario. Thank you, Christian, and well, have a nice weekend.
Thank you for inviting me and giving the opportunity to talk here. So it was nice to see again some of your faces. Some of you are now from Grissemeyer, and yes, I would also wish you. I mean, now it's starting to get evening here. So, but I wish you a nice day today. Okay.
Thank you.
Bye.
Thank you.
Thank you.
Bye.
Bye.
Bye. Take care.